Hi everyone, welcome back. We are talking about derivative-like operations for vector fields, and we're going to continue discussing those types of things in this video here, which is on the curl of a vector field. So before we get to the curl, let me remind you of some derivative-like operations that we've already considered. And the first one was the gradient of a scalar field. So I could take this, and everything is really related to this del operator. So this was the gradient of t. Okay, and we also had then in the previous, just recently in the previous video, we had the divergence. So this was the gradient, and this is the divergence. And just to remind you, the gradient gives you a vector field back. So even the gradient of a scalar, t, gives you a vector field back. And the divergence, because it's a dot product, the divergence actually gives you a scalar back. So you'll always have to kind of keep these things in mind. Am I expecting a scalar, or am I expecting a vector in return? Now, related to the divergence, or it's akin to the divergence, I guess you would say, is the curl of A. And the curl of a vector field is simply the cross product with the del operator instead of the dot product. So if we take del cross A, or we could write curl of A. So this is, and again, this is just called the curl. Right? So if you see del cross A, you would read that as del cross A, or you would read it as the curl of A. Now let us discuss the interpretation of this. The magnitude of del cross A, because remember this is a cross product. This is a cross product. So when you cross two vectors together, you get a vector in return. So that's one of the big differences between curl and divergence. You get a vector in return. So the magnitude of del cross A at a point is a quantitative measure of how much A curls or circulates around that point. So let me give you an example. Let's say we have a point P and we have a vector field that's like circulating around here, right? It's a measure of how much circulation you'd get. So maybe you've kind of seen like a pinwheel. Usually the wind pushes the pinwheel. If you put a pinwheel at point P and you kind of anchored it so that it couldn't move as a whole, but the blades could still move, and if those pinwheels are going to move, or the wings of the pinwheel would move, then you have some circulation there. You have some non-zero curl. All right, and you can directly contrast that with a vector field, maybe a vector field B here. This also has zero divergence, by the way. But maybe this is vector field B. This is not curling at all, so this would have zero curl. All right, so that's the magnitude. It's a quantitative measure of just how much circulation you have of your vector field around point P. And let's talk about the direction of the curl, and for that we're only going to talk about A because this has a zero curl, and B has a zero curl, so there really is no direction. So for A, the direction is the axis of rotation, and we can use the right hand rule just kind of in a different way. It all ends up being the same thing actually, but what you can do is you can take your right hand and you can curl your fingers in the direction of A. So I'm doing this right now. You should be too. Curl of your right hand, take your fingers and curl them in the direction of A. Your thumb points in the direction of the curl. So the axis of rotation is out of the page or into the page, or out of the screen into the screen. Okay, that's the axis of rotation. So there are two possibilities. Well, is the direction out or in? Well, if you did this right hand rule correctly and you circulated your fingers around P in the direction of A, then you'll notice your thumb is pointing out of the screen if you did that correctly. So in fact, that's the correct answer. The direction of the curl of this vector field is out of the screen in this case. All right. Now, related to the curl, and if you recall, there was a divergence theorem, and the divergence theorem related a closed surface integral with a volume integral. There is also a similar, analogous theorem for the curl of A, and it's called Stokes theorem. Stokes. It's one of those weird words that theorem that gets S apostrophe S because the gentleman's name was Stokes, and so for proper names you have Stokes and then apostrophe S. All right, and Stokes theorem says, and we're not going to prove it, the proof is in my notes and in textbooks. Stokes theorem says that the circulation, remember the circulation around a closed path or closed line is given by this thing, but it's also equal to an integral of the curl of that vector field over the surface that's enclosed by L, right? Okay, so let me just give you kind of a graphical depiction of what this is saying. So you have a path, okay, in 3 dimensions, but maybe this is just 2 dimensions because that's all I can really draw for right now. So here's our path. So we want to know the circulation around this path L, and this is in some sort of vector field, right? So it's really the circulation of the vector field around this path L. So we can compute this integral here, the left side of that equation, or Stokes theorem says that you can consider the curl of the vector field A and then compute a surface integral instead. So what surface is that? Well, that's this surface. It's the surface enclosed by this closed path. Okay, and the reason we would need such a theorem, similar to divergence theorem, is that the left side comes up a lot in physical situations, and the right side might be easier to compute. And we'll have plenty of applications, when we get into the material proper, the electromagnetics proper. All right, I'm going to erase some of this here, so feel free to pause the video as always if you need to jot some things down. Let me talk about the properties of the curl. And we've already said this, I guess, the curl of a vector field is another vector field. Another vector field. So again, why is that? Well, that's the cross product. If you take the cross of 2 vectors, then you get a vector back. So this is not what happened for the divergence, because the divergence was a dot product. We got a scalar back. Now the divergence and the curl are somewhat opposites, and what I mean by that is the divergence of a curl is 0. The divergence of a curl is 0. So mathematically we would write this: divergence of a curl, like that. Okay? Divergence of curl is 0. And also, another property is that the curl of a gradient of a scalar field is 0. So if we did del cross, so that's the curl operation, then the gradient of a scalar field, this would give us 0. The gradient has no curl. And for brevity, I'm going to forego the proof of these three things. The proof of the last one is in my notes, and I'll leave you to prove the first two if you would like. What I want to concentrate on is the calculation of the curl. So in Cartesian coordinates, let's say we have the curl of vector field A, and let's say vector field A then in Cartesian coordinates has an x component, a y component, and a z component. Okay, like that. So how do we calculate a cross product again? Remember? So we put ax up there, we put ay up there, az. Now, the del operator was, it's hungry, it's just got these operations: the derivative operation, the partial versus x in the x direction, the partial versus y in the y direction, and the partial versus z in the z direction. That's the del operator. And then A has components ax, ay, az. Okay, so how do we compute that? Well, remember that now we take a determinant. So we start with ax, and we ignore everything below and in the same row as ax, and so we just have this 2 by 2. We take the determinant again there, so we would take daz dy minus day dz in the x direction. Okay, then we would add to, or subtract, I guess the next one is subtract, right? Because then we consider ay and we subtract that one, and we ignore everything in the same column and in the same row, and that leaves us another 2 by 2 matrix. And we'd have daz dx minus dax dz in the y direction, and then plus, and then we would consider az, and we would ignore again everything in the row and the column of az, and we would have a 2 by 2, and we would say day dx minus dax dy in the z direction. So that's how you would calculate the curl in Cartesian coordinates. Now let's look at spherical coordinates, and I'm just going to erase this. So I'm not going to prove why this is, but it's still related to, we talked about cylindrical coordinates, and we talked about how the arc length is related to the radius, and so we have to take the radius into account and normalize and so forth. So I'm not going to prove this, but it follows straight from what we've already said with cylindrical coordinates. When we take the curl in cylindrical coordinates, we're going to have to normalize by 1 over rho, and what we put up here is a rho, and then rho a phi z, az, and then everything, at least in this row, is straightforward. And then in the next row, we need a rho, and then we're going to take rho times a phi, again for those same reasons that we've been talking about. So this is how you calculate the curl in cylindrical coordinates. And the things you need to watch out for here, I'm warning you, is this here. We take 1 over rho times that determinant. That's easy to forget because you spend all this energy calculating the determinant, and you're like, yes, I just did it, I'm finished. No, you're not finished. You need to divide by rho. Watch out for this guy because that's not there in Cartesian coordinates. And watch out for this guy. All right, now let us talk about spherical coordinates, how to calculate the curl in spherical coordinates. Again, actually, before we get to that, don't memorize this. Don't memorize this. Write it down in your notes. Bookmark it in your textbook, whatever you need to do to be able to refer back to it quickly. I don't want you memorizing these things. It's not worth it. Nobody memorizes that, except for professors. Okay, so now the curl in spherical coordinates. So we're going to normalize by this thing. Again, these slight changes are coming from the fact that we have two angles, phi and theta, and so we have to do this normalization by the radius. All right, so in the top we're going to put AR, RA theta, and then R sine theta A phi. And then in the next row, we're just going to have d dr as you would expect, the partial, d d theta as you would expect, and d d phi as you would expect. So that's good. And then down here we're going to have AR as you would expect. Then we're going to have R A theta. I don't know if you expected that or not, but maybe you did. And if you did, good for you. And then here we have R sine theta A phi. That's how we're going to calculate the curl in spherical coordinates. Spherical chords. Okay, so some things to watch out for here, is this guy. Again, once you calculate the determinant, you still need to normalize by this thing. Watch out for this R. Watch out for this R sine theta. Watch out for this R. And watch out for this R sine theta. Okay, so that is the vector curl. And we're actually almost done. We're almost done with vector calculus. We have one more short derivative-like operation. That's called the Laplacian, and that is coming up next.